It is a GATE 2020 question from the subject called compiler design. Here two grammar productions are given, first and second. And first production with two alternatives, second production is one alternative. Here the question is number of reductions taken by a bottom-up parser while accepting the string AAADBBB is a string. So means how many steps are required, means how many number of reductions are required to parse the string given. Here I am writing the string AAAD and triple B. Here the approach to be used is bottom-up parsing technique. Bottom-up parsing technique construct a parse tree starting from the input and reduce this input to starting non-term. Reduce this input to starting non. This process is called reduction process. We call it is reduction process. In the reduction process, it requires to identify the handles in the sentential form. Here I am using one word called handle. Handle is nothing but RHS of a production. RHS of a production need to identify in the input sentence, in the derivation step. That RHS of a production need to be replaced with its left hand side. This process is called reduction process. We also called it is handle pruning technique. What it will do in handle pruning is it will scan the input from left to right and stop the process. Scan the input from left to right and scan the process as soon as it sees RHS of some production. Here for this step, at this step, I can find, when I'm scanning from left to right, I can find a handle D in the input AAAD triple B. So because D is a RHS of a production S tends to B, so that this D is going to be replaced with S. This is called a reduction process. We also called handle pruning. Now after replacing the D with S, now my input string is AAASBBB. First reduction is over. This is called reduction number 1. Now it will repeat the process of scanning the input from left to right to identify the RHS of some production. It scans the input from left to right and identify the RHS of some production. Here I found RHS of some production B tends to B. Here S tends to D, okay. B tends to B. It is a second one. Now it requires to replace this B with its LHS capital B. So the string becomes AAAS. This B is replaced with capital B, and we also have two B's. Again the process is repeated, scanning from left to right and stop the process as soon as it finds a handle. Now here it finds a handle called S tends to ASB. As soon as a handle is found, perform the reduction, means replace RHS with its left hand side. After replacing RHS ASB with S, will have the sentential form 2As. This ASB completely is replaced with single S and we have 2Bs. Again repeat the process of scanning the input from left to right and stop as soon as you find a handle. Here in this situation the handle is B tends to B. This is the fourth step in the reduction process. So after reducing AASBB, now the resultant sentential form in the process is AAS. This B is replaced with capital B and small. Now again repeat the process, scan the input from left to right. Here we find the handle S tends to ASB. This is the fifth step. Now replace S tends to ASB, means replace ASB with S. Now the resultant string is ASB. Again repeat the process, scan from left to right, stop the process whenever the handle is found. Here the handle is B tends to B matching. This is a sixth step. Replace this B with its left hand side capital B. The string after the reduction is AS capital B. Again the process is same, scan the input from left to right and stop whenever the handle is found. Here in this step we have a handle ASB matching with the production, S tends to ASB. Now this is the seventh step, and prune the handle means replace its RHS with left hand side so that it is going to be reduced to S. Here in the bottom up parsing technique, we have to start with input and reduce this input in a series of handle prunings to the starting non-terminal. This complete process we call it is reduction process. In this reduction process, to reduce this input to the starting non-terminal, how many steps are required? 1, 2, 3, 4, 5, 6, 7 steps are required. So answer for this question will be 7. Here the question is, consider this following statements. There are 3 statements are given, 1, 2, 3, and the question is which of the above statements are true. Among the 3 statements, which statements are true, we have to decide it. Just understand the first statement. Symbol table is accessed only during, here you observe, the symbol table is accessed only during lexical analysis and syntax analysis. Here this statement is directly I can say it is false statement. Why? Because symbol table not only used for lexical analysis phase and syntax analysis phase, it also will be used by other phases, because all the phases is going to be connected with symbol table. So because all phases are connected with symbol table, this statement is false. Now coming to the second statement, compilers for programming language that supports recursion necessarily need heap storage. It requires necessarily for heap storage. Just understand, recursion does not require heap storage. Heap storage is required for dynamic memory allocation, and actually recursion requires a stack allocation. As an example, suppose I do have a main function here, and main is calling function A is calling function B calling function C, and so on. So here how this program execution does. First execution starts with the main. Now it is calling a function, means after executing this a function, control should return to a function, means on return it requires to execute the further statements after this function call. So it needs to maintain some information about that main function. So first it will push us one activation record for main into the stack. Okay, we call it is activation record. Activation record contains information about local parameters, formal parameters, local variables, return values, return addresses, right? So many information is to be maintained, means activation record specifies information pertaining to one execution of a function. Okay, means before control leaves, it maintains one activation record in a stack. Okay, next as soon as it leaves control, now it is executing the a function. Now a function is calling b function. Okay, a is calling b function. So means it is to leave the control from this place. On return it should execute the further statements. So it requires to maintain some information about this function a. So it has to push one activation record for function a before it leaves controls to b function. After it moves to b function, it execute all the statements of b. After execution it should return to this one. So how it knows the return address is at this place? By popping the activation record of a. By popping activation record of a, it will returns to this, so that all local variables, global variables, whatever is needed for this function to execute will be returned, so that this function will get executed. On return, again it will pop this main and restores whatever the values that are required for execution of the main function and continue. It means recursion does not necessarily to need heap organization. Heap is an alternative, we can accept it, but heap is not necessarily, because recursion is mainly required to have stack allocation, means stack is used for recursion. So that we conclude that the second statement is also false. Okay, second is also false. Coming to the third one, errors violating the condition. Any variable must be declared before its use. Any variable must be declared before its use, detected during syntax analysis phase. Any variable must be declared before its use is not detected by syntax analysis, instead it is detected by semantic analysis phase. Okay, it is detected by semantic analysis phase. Why? Because if you have some statement a equal to a plus I, later we have int a, this is not detected during the syntax analysis phase. In the syntax analysis phase, here we have a equal to a plus I semicolon. These are the tokens. These tokens will be grouped according to syntactic structures, so that at grouping syntax structure doesn't require whether the variable a is declared or not. It doesn't require. So that any variable must be declared before its use is not detected by syntax analysis phase, so that the statement is also false. So here all the three statements are false, so the answer will be option D. This is a question in GATE 2020 from the subject compiler design on syntax directed translation. This is based on L attributed definition that uses synthesized and inherited attributes. First, understand the question. Consider the productions A tends to PQ, and we have A tends to XY. Each of the 5 non-terminals A, P, Q, X and Y has 2 attributes. We call S is a synthesized attribute. So what is synthesized attribute? Synthesized attribute whose value is going to be computed from its children. Children means, suppose A tends to BC is a production. The value of A means, if you attach some attribute S to A, B, C, so that value of this parent you can determine from its children's. Then we can call S is synthesized attribute. Just keep in mind, synthesized attribute whose value is determined based on its children's. And we also have here one more attribute we call I. I is inherited attribute. Inherited attributes will determine its value from parent and are siblings of a node. It does mean that, suppose I do have a production A tends to BC, and if I draw a dependency graph for A tends to BC, and assuming I have an attribute called I, suppose I do have a semantic of CI. I is computing from its parent and sibling. So means here we have a semantic of CI whose value is determined from parent as well as sibling. Then we call I is inherited attribute. Okay. Coming to the question, here they have mentioned 2 rules. This is a rule 1 and rule 2 based on the productions of A tends to PQ and A tends to XY. Rule 1, the first rule is Pi equal to AI plus 2. Pi equal to AI plus 2 means it is a rule on the production A tends to PQ. If I have a syntax tree for A tends to PQ production, you can find A tends to PA here and P and Q here. And here it using one inherited attribute I, here also I, and no attribute is attached to Q. And observe this rule, Pi equal to AI plus 2 means the value of Pi, it is computing from its parent. And one more is Qi equal to Pi plus AI, means one more dependency graph I am drawing, AI, Pi, Qi. When you see the dependency graph for the second rule, Qi equal to Pi plus AI, Qi means this attribute is determining its value from Pi, we call sibling, and also AI from the parent. This is inherited attribute. And we have one more rule, AS equal to PS plus QS. Again I am drawing A, P, Q. AS synthesized attribute, PS and QS. If S is synthesized attribute, its value is computing from its children, means AS getting its value from PS plus QS. So this is also correct representation. This is represented by rule 1. Now we'll see the dependency graphs for rule 2. Here I am drawing dependency graphs according to the rule 2. This rule 2 is for the production rule A tends to X, Y. Now here the rule is Xi equal to AI plus Ys. Xi equal to AI plus Ys. Means it is determining its value from AI and also from Ys. And one more is AXY. Here Yi equal to XS plus AI. Yi equal to XS means from sibling and AI from parent. We call I is inherited attribute. Now coming to the question, which of the following is true? Here the question is for L attributed definition, means neither rule 1 nor rule 2 is L attributed. Both rule 1 rule 2 are L attributed. Only rule 1 is L attributed. Only rule 2 is L attributed. Now question is about L attributed. First we'll understand what is L attributed definition. What is L attributed definition? Here in L attributed definition, it uses synthesized attributes and are inherited attributes. In both rule 1 and rule 2, it is having both synthesized attribute S and inherited attribute, both are there. And the second condition is if we have a production of the form A tends to x1 x2 dash dash xn, then the semantic rule for some I, it is to be computed. Okay, just observe some semantic rule of I, it is to be computed from its parent and are siblings that are there to the left of that xi, not to the right of xi. Means when you see this is x1 to I minus 1 and xi, so means xi should get values from parent and also from left siblings, but not from right siblings. That's the name is called L attributed. Means the distribution is from left to right, but never from right to left. This point also to be satisfied. Okay, right to left is incorrect, left to right only correct for L attributed definition. Now we'll check. Here from parent it is correct. Here from parent and from left sibling, it is left to right evaluation, correct. This is synthesized attribute, no issue at all. And means rule 1 is L attributed. Okay, coming to rule 2, here you observe xi computing its value from its parent and from right sibling. Observe xi is getting its value from parent A, this is correct, and from ys means it is deriving its value from parent and from right sibling, means evaluation is from right to left. This is not allowed in the L attributed definition. So that rule 2 is not L attributed. It is not L attributed, but rule 1 is L attributed. So that the answer is only rule 1 is L attributed. That is an answer is option C.